Okay, so we'll go through. Right, so before we start, just to check your understanding, can you try this exercise? Right, don't spend too much time. And for all these recordings, you'll be viewed by you only, right? You won't be shared anywhere. You'll be a private playlist on YouTube, right? If let's say you are unsure, you can just put a dash, right? Finish already? Yeah. So this is just a check for me to see, right, how much you understand. So actually all this that's below here is incorporated into the new syllabus, right? In the old syllabus, students weren't required to know, but for a new syllabus, actually all these are very, very important for organic chemistry. I think that's why they incorporated it into a new system, right? So let's begin with introduction. A lot of students just neglect this chapter because they think that introduction sounds easy, correct? Usually I can just skip introduction and can still do well, but the fact is there's a lot of important stuff inside here that you cannot skip, right? You will see these important stuff as you go through. So first, organic chem deals with mainly carbon, hydrogen and other non-metallic elements. So there are students which ask me, are these two molecules organic? What do you think? No, they are not organic. Right? You must have carbon and at least hydrogen in it for it to be organic. For this, it's only carbon and oxygen, it's not organic. Why is this concept important? Now, if let's say I give you, I'm not sure if you have seen such questions before. I give you a molecule X, and then I ask you to name in the reagents and conditions to convert to Y. And the question usually says that, okay, name the organic reagent. Do you think you can name metallic reagents? Like for example, let's say we have NaCl, something like this. No, you can't, because this is obviously an organic reaction. This sodium chloride is inorganic, just like your carbon dioxide and carbon monoxide, they are inorganic, right? So this is why the concept is important, although it seems very trivial, right? However, organometallic reagents can also be used in organic reactions, just like the word organometallic suggests. It's made up of an organic counterpart and a metallic counterpart, right? Can you tell me which one is the organometallic reagent for this reaction? You don't have to know the reaction, right? You just have to spot the organometallic reagent.
MgBr.
Yes. You might think that, hey, I've never learned this. Will it be tested? Obviously, yes, right? Because this reaction involves the concept of what you are going to learn in nucleophilic addition, right? The concept is the same thing, just that they form you one new reagent, right? So this is actually known as your organometallic reagent, because you have your organic CH3, you have your metallic Br, right? Connected to organic Mg connected to a Br. You might wonder, you have a metal, correct? And then you have a non-metal, and then you have a non-metal. Shouldn't they form ionic bonds? That's what you learn in O levels, right? You have a metal, non-metal, they'll form ionic bonds. But for this, no, right? All this boils down to your chemical bonding. Why does it form covalent bond? The reason is because of electronegativity difference, right? Just a quick recap. If let's say the electronegativity difference between two elements, this is just a rough guideline, right, is greater than 1.8, then it's mostly ionic, right? If the electronegativity difference is less than 1.8 and maybe greater than 0.4, you will be polar covalent. And anything less than 0.4 means it is non-polar, right? So for this, we can call it a polar covalent bond, right? Do you still remember electronegativity?
Yeah.
What's the definition?
The tendency to attract electrons to
Itself,
yeah.
right? So it makes sense to think that if let's say one of the element, its electronegativity is so great, the bonding electron will be so close to itself that it just resembles an ionic bond, right? So this concept is from electronegativity, right? We are now only interested in the structure, not the chemistry behind it yet, right? So now carbon can exist in various oxygen states and different forms, right? So here are some different forms: carbocations, carbanions, carbenes, and radicals, right? So for your syllabus, you have to know what is a carbocation and carbanion and how they are formed, right? How they are formed wise is behind. For now, we only focus on its structure, right? So let's look at example 1, charge versus oxygen state. Do you think they are the same thing?
They're related, but not the same thing.
They're related. Can they be the same?
Yeah.
They can be the same. For example, sodium chloride, you have sodium plus. The charge is +1, the oxygen state is also +1, right? So for this case, how do we find the oxygen state of the carbon atoms in all of these species? For example, the first one, methane. How do you find the oxygen state of carbon?
H3 plus 1, so this will just will be -4.
Yes, it's -4, right? Same thing, all these boils down to electronegativity. The first step is always asking yourself which one is more electronegative. So if you were to compare carbon and hydrogen, and you should have learned that the trend in electronegativity increases in this way, right? So those that got higher electronegativity are here. So if you were to compare carbon and hydrogen, carbon's electronegativity is 2.5, hydrogen is 2.2, right? So now, for those students who are confused, because for this case it's only carbon and hydrogen, it's quite easy. So how I usually teach them is, whenever you have, provided you already have the structure, right? So first thing, always draw the atoms around it, and then ask yourself which one is more electronegative. So for this case, carbon is more electronegative, and they are sharing one bond, so you just have to put a minus here, plus here. So each of these you can think of it as an electron, right? So same thing for this. So now the final job that you have to do is just circle the electrons that belong to carbon and count how many charges there are. So for these there are 4, so it will be -4. Hydrogen is +1, right? And overall, which relates to the oxidation state, is 0, because everything adds up to 0, right? And then for the next species, I'll just do a demo for you. Same thing. If let's say you're given a species without oxygen state and you are asked to assign the oxygen state, you can do it the same way, right? Minus plus, minus plus, minus plus, right? What about these two electrons? Now you ask yourself, right? Carbon originally got how many electrons? 4, because it's from group 4, right? So now it has got 1, 2, 3, 4, 5. That means the additional electron must have come from somewhere. So what you do now is replace it with a negative charge. And then you don't count this, this one you ignore because you didn't assign any positive plus, right? So for now, carbon will have 1, 2, 3, 4. So this carbon will have an oxygen state of -4, same as your first scenario. This hydrogen still +1, +1, +1. So overall you have -1, right? Because you add up the sums of all of this, right? So you have a -1. So these scientists usually assign this minus to carbon because it's quite obvious that carbon obtained that electron from somewhere, right? So you can either draw it this way, right? Or what scientists, this is what scientists prefer, or another way, which is putting the negative charge outside, right? This is what you learn in your chem bonding. So this is actually known as a carbon anion, right? Because it's anionic species, and later we'll see how it's formed. So can you try and describe the oxygen state and charge for this?
-3 plus.
So what's the oxygen state? You sure? I never draw any lone pair. That means there's no lone pair, right? Carbon is only bonded to 3 hydrogen and nothing else. So the structure of this species is actually like this, right? Same thing, you can approach it in the same way. Minus plus, minus plus, minus plus, right? And then now, if you were to compare this with the previous species, carbon should have how many around it? Should have 4, right? But for now, there's only 3. That means it must have given up one of its electron to somewhere else. So when it receives, you give it a negative. So when it give away, you put a plus. Same thing, circle all of this. So for this carbon, you have a oxygen state of -2. So you have a +1, +1, +1, right, for all of these hydrogen. So same thing, if you were to count overall, it is +1, right? Same thing, scientists prefer to write it this way, by assigning the charge to carbon, right? So this species is known as a carbocation, right? So after you know about this, you should be able to do your true and false question, right? The one with oxygen, right? It's actually the same idea, but you don't have to do it now, right? For the other two examples, you can try out when you're free, right? So next is about hybridization. A lot of students is very confused about hybridization, right? They don't know what's hybridization, they don't know why it occurs. So most schools don't really teach why hybridization occurs. They only teach how hybridization occurs. Am I right? They'll just go straight into hybridization, telling you all the hybridization states, blah 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 blah, right? But for me, I prefer to go from the basics so that you can appreciate why hybridization is necessary, right? So by now, I assume that you know how to draw the relative energy levels, which is your atomic structures lecture. Sketch the respective atomic orbitals. Just the S and P will do, right? As long as you know that S orbital is spherical, P orbitals are, draw the axis, P orbitals are like that, correct? With two different faces. And lastly, describe a covalent bond as sharing of electrons. These are all that you need to understand hybridization. So now let's look at why hybridization is necessary, right? So if you were to consider the following scenarios, and if you were to only use the very, very fundamental valence bond theory, right? So actually, this hybridization theory arises because valence bond theory, which is your most fundamental theory, couldn't explain some of the phenomena. So that's why scientists, which is Pauling, decided to come up with this new hypothesis known as hybridization. Of course, hybridization is not a physical process that we can observe. It's just something that's proposed to explain this, and it works well, right? So let's only focus on valence bond theory for now, right? So let's say we have elements carbon and hydrogen. So what will be the expected stable species formed, right? So in order to find out what's the expected stable species, let's say last time people don't know about structure of methane, CH4. They know it's CH4, but they don't know the exact structure, right? So first thing what we'll do is we'll draw the energy levels of carbon. For this, you shouldn't have any problem, right? So how many electrons are in 2s? 2, right? How about 2p?
2 also.
Is it like that? There. Is it like that?
No.
Up, both are up. This is your Hund's rule, right? Remember your Aufbau principle, Hund's rule, and your Pauli's exclusion principle, right? So now this is carbon, correct? Agree? So now you have learned in O levels that if let's say you want to form a bond with hydrogen, carbon need to share one of its electron with one hydrogen, right? One electron, not one lone pair, which means that since it has this energy level, at most it should only form 2 covalent bonds, right? Does your school teach this? No, right? Okay, good. So carbon can only form 2 covalent bonds because obviously it has got only 2 lone electrons, right? That's the expected stable species if you were to only use valence bond theory. But obviously, you know that CH2 is not stable. Why? Because if you were to draw the structure, it doesn't have 8 electrons, you only got 6. So obviously, there's something wrong with this bonding picture, right? So that's the first problem with this valence bond theory. From now, I will call it the number of bonds problem, because obviously, it forms a different number of bonds than expected. Than actual, right? That's the number of bonds problem. Next, we look at what we call the bond angle problem, right? But that one is only for this case lah. Later on we'll come back to here. So same thing if we were to use the same analysis for oxygen, right? Oxygen is from group 6, so it's got 6 electrons. So it's got 1, 2, 3, 4, 5, and 6, right? And then you might think, okay, water is H2O, obviously, right? So in order to form a covalent bond, oxygen must bond to 2 hydrogens, which means that it needs 2 electrons. So just nice, what? This structure, 1 for each hydrogen, isn't it? So why is there a problem?
Still lone pair.
Lone pair, how many lone pairs are there? 2 what? Why 2? Yeah. 2 what? Correct. Correct, 2 what? 2 lone pairs, right? Chemical bonding, 1, 2, 3, 4, 5, 6. Yes, got 6. Correct. So these two lone pairs, why is there a problem? These two are lone pair, why cannot? It looks like it can, right?
Yeah.
Okay, now we'll see what's the problem, right? So assuming that it forms H2O without any hybridization, think of the second one, right? The second point, sketch the respective atomic orbitals. So if we were to sketch the atomic orbitals all on one axis, right? I'll try to not make it so confusing. It's behind and in front. So this is your 2s and your 2p orbitals, right? From just now, the energy level, we know that one of the 2p orbitals got 2 electrons. So we just put 2 electrons here. The other one got 1 each. 1 here, 1 here. Right? Correct, huh? And then your 2s, I won't draw lah. Later it's too confusing, right? So now, if let's say hydrogen were to form a bond, you need to share one of these electrons with oxygen, right? So what you do is that one hydrogen should approach like that and form a covalent bond. And another hydrogen should approach along this axis to form a covalent bond. Makes sense, right? This bonding picture. But you should have learned from your atomic structures that the p orbitals are at what angles to each other? Right angles, correct? Because one of them is along x, one of them is y, one of them is z. So you expect the bond angle to be 90 degrees, obviously. Which means that you would expect these species to have a bond angle of 90 degrees, right angles. Does water have a 90 degrees right angle, bond angle? No. What is the bond angle? 107, right? The bond angle is actually 107 degrees. So now, this again doesn't explain the 107. Because if you use valence bond theory, you should predict a bond angle to be 90 degrees. How can you have p orbitals that's wider from each other, correct? Something strange must be going on. And apart from that, like what you mentioned about the lone pair, right? For this, the lone pair is on p orbital. For this, the lone pair is on in the s orbital. So obviously, you know that p orbital and s orbital are different in energy, which means that these two lone pairs should be of different energy. Which means that more of them, one of them, which is this, should be more reactive because it's higher energy, more unstable. So therefore, it should be more reactive. And scientists have found that these two lone pairs are actually equivalent in terms of energy, which doesn't make sense if you use valence bond theory once again, right? And the last problem they face is about the structure as well, right? So how are these two lone pairs situated if let's say you want to draw the structure? You can't draw like that, because if you draw like that, you are assuming that they are equivalent and they repel each other by the same amount. But for this, no. This lone pair is in the inner shell, which is your 2s, and it's spherical. Spherical means it should be found anywhere around here, right? But it's not. So this is another problem. But the main problem that you should see is actually the bond angle problem, right? This one is quite obvious. So call this kind of problem from now on the bond angle problem, right? So although the expected stable species is H2O, the expected bond angle is not what you predicted, right? So for this, the blank is H2O, and the expected bond angle is actually 90, but you know that the actual one is 107, right? Same thing for methane. If you were to apply this same concept to methane, you will know that methane, which is your CH2, will also form a 90 degrees structure, correct? Because what is different is just that you don't have this lone pair, correct? So it should also form a 90 degrees structure, but in fact it is 109.5, which is your tetrahedral. So this is also another weird thing about valence bond theory, right? So you can pretty much see that valence bond theory actually fails to describe the structure of even simple molecules like this, right? So that's why scientists have need to use the hybridization, more advanced theory to explain it, right? So just to check your understanding, so can you tell me what's the problem of using only valence bond theory to describe BH3? So you can draw the same thing, right? remember, always, in order to explain the number of bonds problem, you have to do the first one. If you want to explain the bond angle problem, you have to do the second one.
If you use the valence bond theory, you have 1H,
Yes,
2pH, but
correct.
only
That's 3.
pH 3.
Okay, and obviously, as long as you have the number of bonds problem, you should have the bond angle problem as well, right? So this is why you can't use valence bond theory here, right? So now, in order to get rid of problems faced as well as a bunch of other problems which is not described here, the concept of hybridization was introduced by Pauling. So hybridization is the mixing of orbitals to give a set of orbitals equivalent in energy to describe the inadequacy of valence bond theory. So you'll learn about the how of hybridization first before we see how these problems can be solved, right? So before we go into hybridization, there are 2 rules that you have to keep in mind, right? So first is the number of electrons before and after hybridization remains the same, which I will call it the conservation of electrons, and then the second one I will call it the conservation of orbitals. These 2 can never be destroyed, right? It's just like your energy. So let's look at sp3 hybridization first. So just take note that it's not a stepwise procedure, it's just described in a stepwise fashion to help you to understand, right? So the step 1 of hybridization, let's take carbon for example. Here is the energy level. First step is the promotion of an electron from a 2s to 2p. So now you will have 4 orbitals with single electrons, right? So step 2 is the hybridization of 1 2s with 3 2p orbitals. So if you observe from here, we never touch 1s, correct? So 1s will remain where it is in terms of energy level. For this, you must illustrate clearly. For 2s and 2p, since you are mixing them, the resultant orbital should be somewhere between them, right? The energy levels. And originally, you have 1, 2, 3, 4, 5 orbitals. Afterwards, you also have 5. Before that, you have 1, 2, 3, 4, 5, 6 electrons. Afterwards, you still have 6, right? So after hybridization, you realize that 1, 2s, and 3 2p orbitals are replaced by 4 sp3 orbitals. Each of these known as an sp3 orbital, right? And they will arrange themselves in a tetrahedral geometry to minimize repulsion, right? So in ethane, this is the structure of ethane. 2 sp3 carbon will overlap to form the sigma bond, and the other 3 hybridized orbitals will form sigma bond with your 1s orbitals of hydrogen, right? So now, why does this solve the problem of what I face in valence bond theory? So originally I already described why valence bond theory failed. So now if let's say these were to hybridize, after hybridization you have 4 orbitals, right, of equivalent energy levels. So when you have these equivalent energy levels, right, we analyze the same problem once again, right? So carbon, in order to form, so sp3, 1s. So carbon, in order to form covalent bond with hydrogen, you need to have lone electrons, right? So for now, just nice, it has 4 lone electrons, so just nice, you can bond to 4 other hydrogens. So that explains your structure of CH4, and that solves your number of bonds problem. And then next, bond angle problem. If you were to look at the valence electrons, which is these, this is your inner shell already, right? So now once your s orbital and p orbitals are gone, are replaced by sp3, now you have 4 sp3 orbitals, and you have learned your chem bonding that these orbitals will minimize repulsion by placing themselves as far as possible, right, to form the tetrahedral geometry, and this tetrahedral geometry is 109.5 degrees apart, right? So this also explains your bond angle problem. So very good, sp3 explains everything, right, this hybridization. So there are other examples of sp3 hybridized atoms, which is this and this, right? So how do we work out the hybridization state of this? Let's say you don't know that it's sp3. Same thing, we can apply the same concept, right? 1, 2, 3. These are 2s, these are 2p. So nitrogen is from group 5. You have 1, 2, 3, 4, 5 electrons, right? So you know that for ammonia, which is the simplest nitrogen and hydrogen species, nitrogen will form 3 covalent bonds. So it should form using the valence bond theory. But of course, there will be a bond angle problem. So in order to solve the problem, same thing. First, you promote electron from 2s to 2p, right? It's okay if you already have all of them filled. This is not a requirement, empty orbital is not a requirement, right? So same thing, you promote this to anyone here, right? You have this. Wait, yeah, correct. You have these species, right? 2s and 2p. So afterwards, hybridization, mixing all of them together, right? So before you mix, you have 4 orbitals. After you mix, you also have 4. Before you mix, you have 1, 2, 3, 4, 5 electrons. After you mix, you also have 1, 2, 3, 4, 5 electrons, right? This is your sp3. So same thing, one of these will bond with hydrogen, and these will be the lone pair on nitrogen. And it also explains the bond angle, because this is tetrahedral still, just that one of them is replaced by lone pair, and because lone pair is closer to a nucleus, it will exert greater repulsion, so it's actually slightly smaller than 109.5. This also explains the structure as well as the number of bonds, right? I will not work out this one. You can work out for yourself, right? Let's look at sp2 hybridization. Same thing, step 1, promotion of electrons. This is omitted because it's quite straightforward already. So step 2 is the hybridization of 1 2s with 2 2p. Just now is 1 2s and 3. This is 1 2s and 2 2p, right? This orbital is not affected, so if you were to compare these two, you realize that for the orbital which is not affected, we don't touch the energy level. We remain where it is. For the other 3, they will go to somewhere in between, right? Same thing, these two must be conserved. Next, if you were to look at the geometry of these orbitals, so after hybridization, 1 2s and 2 2p orbitals are replaced by 3 sp2 orbitals, which arrange themselves in a trigonal planar geometry, right? So now if we were to look at the overall bonding picture, originally it's like that, correct? You have your 2s and your 2p. So let's say this is your pz, let's say we didn't touch your pz, that means it should remain where it is, makes sense, because you never touch it, which is this orbital. And the only thing that you touch is these 2s, this, which is your py, and your pz, right? Sorry, px. So these 3 orbitals combine to form sp3 orbital. So for sp2 orbital, sp2 orbitals are in this shape, right? So since you only touch these 3, only these 3 will disappear. This one will not disappear, right? So the final bonding picture is just this one which is left untouched, combined with the 3 new orbitals. Another one which is here, right? That's how you get this bonding picture. So remember, although it's not illustrated here explicitly, you should always know that there's a small lobe there, right? Just like in this case. And later we'll compare the lobe of sp3, sp2 and sp and see why are they different since they have the same shape, right? So now if in each carbon is sp2 hybridized, 2 of them overlap with the 1s orbital of hydrogen, while the third overlap with the sp2 orbital of another carbon. And lastly, the unhybridized sp orbital overlaps sideways with the adjacent unhybridized sp orbital to give the pi bond. And the bond angle around each carbon is 120. So 2 sp2 carbon approach each other, you form a sigma bond here, and this unhybridized sp orbital overlaps sideways to form a pi bond. So what you have learned in chem bonding, which is the head-on overlap and sideways overlap, still applies here, right? Let me ask you, for one pi bond, how many bonding regions you have? 2, 1 pi bond, this is 1 pi bond, but there are 2 bonding regions. So what does it mean? Does it mean that 2 electrons reside on top or below or 1 each? Yes, it can be anywhere. It can either be both on top, both below, or 1 each. You cannot predict, right? So that's why you have 2 bonding regions. So other examples of sp2 hybridized atoms are illustrated here. You can same thing work out why is sp2 based on this example, right? So let's move on to sp. Right. Just for information, I usually don't like to ask things that's already in the notes, right? So usually for all the tests that I give my students is open universe, means you can Google or whatever, right? Because for a good student, if you understand a concept, you don't really have to open the book, right? Because you cannot find such examples in the book anyways, right? So next, lastly, sp hybridization. I'll just briefly go through this because it's rather similar to sp2. Same thing, you never touch these 2 orbitals, they remain where it is. You only touch these 2, they will remain somewhere in between, right? So after hybridization, sorry, this should be a wrong diagram. It's the same as this. I think I included a wrong diagram, but nevertheless, you can refer to this, right? So ignore this for now. I'll update my notes. So after hybridization, same thing. If you were to apply the same analysis, right, you realize that, okay, I never touch this orbital, I never touch this orbital, and I only touch this, which is your px and your s orbital, right? So since you only touch this, only these two will be gone, and you'll be left with something like this, with a small lobe, right? So this one should replace this picture, right? Nevertheless, in ethyne, each carbon is sp hybridized. One of them overlaps with the 1s orbitals, while the other overlaps with the sp orbital of another carbon. The two unhybridized p orbital overlap sideways with the adjacent two unhybridized p orbitals to give 2 pi bonds, right? So what's different between these two is that this has 2 pi bonds, this has only got 1 pi bond, right? So same thing, these two unhybridized p orbitals, because like what I said, we never touch. Originally they are at right angles, now they are still at right angles to each other, right? Which means that these 2 pi bonds are, if you were to look at it in this way, they're actually like that, right? One of them is here, one of them is left, right, one of them is top bottom, one of them is left, right, right? So this is your sp hybridization. So now let's look at this example 3. Can you try example 3 using what you have learned previously, right? Feel free to refer.
Series for not hybridizing.
That means for just now, when you don't hybridize, you have these two problems, correct? So this is the same, right? Asking what's the problem if you don't hybridize. So let me guide you through. For SF6, if you don't hybridize, there's one very obvious problem, right? Which is a number of bonds problem, we call it, right? And obviously there will be a bond angle problem as well. Same thing for your PCl5. So what should you do? Hybridize, right? So how do you hybridize? You can follow these two steps. First step is your promotion, second step is your hybridization. But for this, it seems that even if you promote, even if you hybridize, there's no way to form bonds with 6 other fluorine, correct? Because obviously there's only 4 orbitals. So what should you do? Recall from the Ken bonding, what's so special about the elements around here and beyond? Yes, precisely, expansion of octet, correct? This is called application.
3D.
So you have 3D. How many 3D orbitals you have? 5. And they are empty, right? So that's the hint. Another problem that A-level students face is that they think everything that the teacher teach is like that already, right? Which is wrong lah. Because the teachers are only teaching a concept doesn't mean they cannot ask other stuff, right? If let's say you only understand what a teacher teach, then how scientists discover new things? It means someone must teach him the new thing, right? And a lot of students think that A-level chem is about memorization, which I believe is not correct, right? Therefore, I emphasize a lot of concept understanding rather than memorization, right? Any problem?
I cannot figure out, like you change the P or the P, right? Then you realize that.
You see, hybridization involves the first step is the promotion of electrons. So if let's say I can solve the problem by promoting one electron, do you think I will promote the other electrons which doesn't affect the structure? No, because promotion of electron is actually quite energetically unstable, right? So now you try to promote the least number of electrons to achieve your target. So let me do the example for SF6. For SF6, you need to have, this is the concept behind it. In order to form a covalent bond, you need to have one hybridized orbital, which is like that, with one electron here, right? So for this case, you have SF6, that means it needs 6 orbitals, right? Using 3D, although we have learned in chem bonding is that they can use, but they can use doesn't mean they will use everything. So for this, you need 6, which means that you need 6 electrons, of course, and 6 orbitals. Make sense, right? So for now, you have 1, 2, 3, 4, 5, 6 electrons, just nice. So you need 6 orbitals. You try to use the least amount of d orbitals. So for this, you have 1 orbital here, 2, 3, 4. So in order to achieve SF6, you just have to hybridize this, right? So in order to hybridize this, the final hybridization state will just be 2d and 1s and 3p. This is the hybridization state of your SF6. You can either write it this way or sp3d, d2 doesn't matter. The concept here is that you must have this d2 component here, right? So same thing, if you were to apply the same concept to PCl5, PCl5 will have a hybrid orbital of dsp3 because you only need 1 since there's only 5 chlorine. Okay, this is the concept behind it. So now the summary of hybridization. So in order to determine the hybridization state of atoms without analyzing it in this long way, you just have to keep the following in mind, right? So for every sigma bond, you will need 1 hybridized orbital with 1 electron in it. For every lone pair, you will need 1 hybridized orbital with this in it. And for every pi bond, you will need 1 unhybridized this orbital, right? So just a very quick demo. If let's say you have these species, and then I ask you what's the hybridization state of this nitrogen, how do you apply this? Same thing, ask yourself how many sigma bonds are there? There's 2, which is here and here, right? So you will need 2 hybridized orbitals with singly charged electrons, which means that you will need like that. Okay, next, for every lone pair you need 1 hybridized this orbital. Same thing, you have 1 lone pair, so you will need 1 hybridized orbital, which is like that. And lastly, for every pi bond you need 1 unhybridized this orbital. From just now, you realize that all the unhybridized p orbitals are higher energy level, right? For the obvious reason. So you need 1 unhybridized p orbital here. And then you count how many hybridized orbitals there are, right? So there are 3, you will be sp2. right? Because it's made of one s and two p. So in total you should have 3 because number of orbitals are conserved, right? So it's easier to check, right? You don't have to do this long method. Okay, so same thing for this. SF6, you should be able to draw SF6 by now. Right? There are 6 sigma bonds. You need 6 hybridized orbitals. There's no lone pair. There's no pi bond. So in total you have 6, and you'll be D2sp3. Right? Actually, this can be derived lah. Right? Just that I show it here. So next, the above method applies to all atoms. Another method exists for carbon, nitrogen, and oxygen centers only. Right? Because this assumes that they don't expand octet or have deficiency. Right? So this is another method which some schools might teach, right? But of course this is the fail-proof method, right? So next is about S character. Hybridization is like blending orbitals of different properties together. So the greater the proportion of the orbital type, then the greater resemblance of character the final hybridized orbitals will look like. So I've drawn all the orbitals here from S to P, right? So this is your SP, SP2, SP3, and the percentage S character. You can see that the more S character it has, the more spherical it gets. The more P character it gets, the more it looks like P, right? So although all of these orbitals have one big lobe, one small lobe, the relative size is a bit different, right? This one you have to take note. So what's the significance of this? Well, if you were to calculate the S character for all of these already calculated for you, some observed phenomena due to S character is that first, your SP-SP CC bond is stronger than SP2 SP2 CC bond. Okay, SP-SP CC bond means that if let's say you have a triple bond here, another triple bond here, this is a single bond, correct? And you should know by now that this is SP hybridized, this is SP hybridized. So this CC bond is actually called SP-SP CC bond. And of course you can have a SP2 SP2 CC bond if let's say these two are now double bonds, right? These two are double bonds, let's say, right? Okay. These two are double bonds, right? It will be a SP2 SP2 CC bond, right? And of course you can have the normal kind, which is the SP3 SP3 CC bond. Okay, so SP SP CC bond is stronger than SP2 SP2 CC bond. Why? Because SP orbital has greater S character, right? You know that S orbitals are closer to a nucleus, right? Closer to a nucleus. So when they are closer to a nucleus, that means your SP orbital, if you were to compare SP orbital, which is something like that, versus your, let's say, SP3, right? This is your nucleus. This is your nucleus. For any electron that's within the SP, you'll be closer to a nucleus. For any electron that's in the SP3, you'll be further away from the nucleus. Closer to a nucleus, that means it is stronger attraction, right? So if let's say I have an overlap of SP and SP, the bond will also be stronger compared to this. Next, this alkyne is more acidic than your alkene, right? So this alkyne is just simply a species with triple bond. So compared to species, this is R, this is H, right? So let's say comparing these two species, we have learned acid base, right? pKa, pKb, all that. So, yeah, right? So if these two were to act as acid, right? The conjugate base sounds familiar, right? They'll be formed with this for this case, or this will be this case, like that. Same thing if you were to work out the hybridization state of this carbon is actually sp. This is your sp2. So same concept, same logic. For this case, you have the negative charge residing at sp orbital. For this, you have a negative charge residing at sp2 orbital. Since the negative charge is closer to a nucleus for sp orbital, it will be more stabilized, which means that this will be more stable, which means that its acid is more acidic than this one, because this, after you form this species, is not stable, less stable, right? So you can also use S character to explain this phenomena. Of course, there are a bunch of other phenomena that you can use this to explain. It's not possible for me to list out everything, right? These are the two examples. So now, can you try example 4? Should be quite straightforward, right?
just saw the SP bonds, right?
Hmm?
Just saw the SP bonds.
Mm-hmm. These tests on your hybridization skill as well as your S character skill. No, I'm not talking about the multiple bond. I'm talking about single bonds. Right?
Oh,
And there won't be a question asking you which bond is stronger. It's quite obvious. Triple bond is stronger, right? Okay, good. Yes, right. Next, example 5. What is wrong with this structure? Suggest better ways to represent this structure. It's related to hybridization as well. And these are some of the common mistakes that students make. Is there nothing wrong? Okay, this is related to hybridization as well. Remember what we talked about? For sp3, the bond angle around the sp3 carbon is 109.5. Around sp2, it is 120. Around sp is 180 degrees. Right? They are linear. Right? It's stated inside here. So for this case, if you were to identify the hybridization state of these atoms, right, you'll realize that for the terminal, the alkene here, alkyne here, it is sp and sp, right? So it should be linear. In other words, this part should be like that. So you should never draw structures like this. Although the teacher, I don't think you'll be marking you wrong because it doesn't really affect your reactivity or whatsoever, right? Same thing for your alkenes. It's 120 degrees, which means that this part shouldn't be straight. It should be bent. And that's how your isomerism arrives, your cis trans, right? And same thing for the benzene ring. Is sp2, a ring of sp2 hybridized atoms, which means that this hydrogen should be 120 degrees, right? Which means that it should be pointing this way and this way, right? Same thing for this. This is a very, very awkward structure, right? This carbon is sp2. You can always apply this to deduce the structure, so you should be like that instead. And lastly, this NH2, which is the same problem as your hydrogen, right? That's why it's weird. Next, example 6. You missed out one carbon, take note. Okay, good, all correct. So now there are some students which tell me that I can deduce the hybridization state of carbon based on the bond angle, and then I drew these two, right? And then they cannot deduce already, right? They think that okay, as long as 109.5 is sp3, as long as 120 is sp2. For this, obviously, is 90 degrees, so they can't do it, right? So the story behind this is just don't think that as long as I have sp2, it must be 120. No, I can make the ring very, very small to restrict it, right? And of course, you forget to label this one, right? There's a carbon there as well. Okay, let's try the last example of hybridization. This is sp2, not sp3. There's a double bond, right?